Hi everyone, it's Kira Garfola with MAT-109 at Greenville Tech. Today we're going to round out what we cover in Chapter 6, and we're going to cover Section 6.5, which is rational functions and rational equations. For most sections, this is the last content that you cover in all of MAT-109, so congratulations. Keep focusing and finish strong though, so that you can finish the course well. So what is a rational function? A rational function is just a quotient of polynomial functions. So you're going to have a function on the top and a function on the bottom. Each of these is a polynomial function, which we've defined before, and each of them is not equal to 0. Can't have a 0 on the bottom because that's the whole thing. And if you had 0 on the top, it wouldn't be any fun. It would just be, y equals 0. So it wouldn't be a very interesting function at all. Rational functions are actually one of my favorite sections to teach, because they can be a lot of fun. It's kind of like a puzzle. There's a lot of things that you have to answer. There's some little rules that we're going to follow, but there can be some really cool, interesting graphs that result. The first thing that's, in my opinion, the easiest to deal with are what we call holes in the graphs. So again, remember that you cannot have a denominator equal to 0. So if you factor the top and you factor the bottom, and there's a common factor of x minus a in the top and the bottom, then there is a hole at the hole in the graph at x equals a. A hole in the graph looks like this. Your graph moves along, blah, blah, blah. It doesn't change anything. It keeps continuing its pattern. But right there, here, it looks like x equals 1. There's a hole because it's undefined there. Let's consider an example. Let's find holes in f of x. So here we have f of x equals x squared plus 3x plus 2 all over x plus 2. The first thing we need to do is factor f of x. Factor the top, factor the bottom. The bottom doesn't need any factoring, it's already there, but the top could be factored. If we factor that top, we get x plus 2 times x plus 1 all over x plus 2. Now look, x plus 2 is a factor in both. So that means that there's going to be a hole at x equals negative 2. So whatever makes this factor 0 is going to be the hole. So x equals negative 2. Now you try. We want to find holes in the graph of f of x equals 2x squared minus 20x plus 48 as our numerator, and x squared minus 3x minus 4 as our denominator. Go ahead and pause the video. I'll give you a minute. And when you're ready, you can resume. So the first thing I did is factor the top would be to take that 2 out. It just makes life easier. Some of you might not do it that way. But if we factor this, we see that we get 2 times x minus 6 times x minus 4 on the top. And on the bottom, it factors to x minus 4 and x plus 1. X minus 4 is on the bottom and x minus 4 is on the top. So we have a hole in our graph at x equals 4. Now holes aren't the only thing that we look at. The next thing that we can look at is called an asymptote. Everybody says that's the most fun word they get to say in college algebra, an asymptote. So asymptotes, if you've never seen them before, are just imaginary lines on a graph that the curve approaches, but it never crosses and never touches. So it comes right up against it and almost kisses it, but it doesn't actually touch it, okay? They can be horizontal and they can be vertical, and then we're going to talk about another example towards the end of this section also. Vertical asymptotes are little vertical lines that the graph approaches and never touches. You can see how this graph comes right up against it here and right up against it here, but never actually crosses it. Or you can have a horizontal asymptote, which is an imaginary horizontal line that the graph, same thing, it approaches it, but it never crosses it. Now, this is a lot of words, but it's here for your reference, and we're going to talk through it. So, if you want to find vertical and horizontal asymptotes, there are just some rules that you need to follow. The first thing you need to do is just what we did to find the holes. Factor your numerator and factor your denominator. If there are any common factors, those are holes. They're not asymptotes. So mark them out and note them as a hole in the graph and set them aside. Any of the remaining factors in your denominator, because remember your denominator can't equal 0, then the zeros of that bottom function represent vertical asymptotes, okay? So anything that makes your denominator 0 that's not a whole is going to be a vertical asymptote. Horizontal asymptotes follow a little bit of a different rule. You need to look at the degree of the top and the degree of the bottom. So if the degree of the top, the degree of your numerator is larger than your degree of the denominator, there's no horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, then y equals 0 is your horizontal asymptote. Now, if the degrees are equal, we actually need to compare leading coefficients. Be careful there, because remember, leading coefficients aren't necessarily your first term, okay, depending how it's organized. It's the coefficient on the highest degree. For anything that we're doing with rational functions, there can only be 0 horizontal asymptotes or 1 horizontal asymptote, okay? At most 1. There are some trigonometry graphs, some other complicated graphs that have more than 1, but for rational functions, anything we're doing in this class, there's 1 single horizontal asymptote. Now that was a lot of information, but this gets easier just working through it with an example. So here's a rational function, and we want to find the wholes, vertical asymptotes, and horizontal asymptotes. So let's start with wholes. Let's start with factoring the top and the bottom. If we factor the top, we see it's x plus 1 and x plus 2. The bottom is x plus 1 and x minus 1. Sure enough, x plus 1 and x plus 1 are the same, top and bottom. So we're going to kind of draw a line through those, leave them aside, know that there is a hole at x equals -1. Okay? Now, for our vertical asymptote, notice the x minus 1 never canceled out. We kind of canceled this one out, right? But x minus 1 is still there. So that's the basis of a vertical asymptote. X minus 1 would be x equals 1 to make that 0. We're going to have a vertical asymptote at x equals 1. So this is a hole. This gives us an asymptote. Now for the horizontal asymptote, we need to compare degrees. We see that the top is second degree, highest power is 2. The bottom is also second degree with the highest power of 2. If we look back at our rules, we'll know that if they have the same degree, then the leading coefficient ratio is our horizontal asymptote. So here our leading coefficient is 1. Here it's 1. So at y equals 1 is going to be our horizontal asymptote. Pause this if you need to make some sense of this. If we graph our example function in our calculators or in our, here I actually used an online calculator so that it was prettier and easier to see. But we can see that y equals 1 is our horizontal asymptote, which is what we found. And we can see here that at x equals 1, we have a vertical asymptote. And it's impossible to tell just by glancing, but there's also a hole at x equals -1. So there's actually a hole right here. Okay, guys, I apologize. Hopefully everything is still here. I had an internet problem here. We all have new laptops and everybody's fighting for Wi-Fi apparently. It says that it's recording, so I'm going to continue. It wouldn't be the last presentation without technical issues, right? Well, hopefully you paused during all of that and you worked on solving this. Let's talk about the solution. The first step that you're going to want to do is factor the top and factor the bottom. There's not much to factor on the top, but we can see the bottom factors. It's the difference of squares. Nothing cancels here. X plus 2 is on the top, x plus 1, x minus 1 is on the bottom. So that means there's no holes. Nothing wrong with that. Not all graphs have holes. That means that anything down here is going to give us a vertical asymptote. So we have two vertical asymptotes. We have it at x plus 1 and x minus 1. Now we see that the top degree is lower than the bottom degree, which tells us that y equals 0 by the rule is our horizontal asymptote. So you can see here there's some rules that maybe some flashcards will help with, but also just getting some practice. If we look at the graph, we see this fun little thing. We have our horizontal asymptote here and our vertical asymptotes here. It's an ugly graph. I would not ask you to graph that. Now, vertical and horizontal asymptotes aren't our only option. We also have what are called slant asymptotes. It would really appear that Greenville Tech does not want me to finish this lecture. I apologize for any connectivity issues you had there. So again, we can have slant asymptotes. They're not vertical, they're not horizontal. They actually follow the equation for a line. This only happens if our numerator is exactly 1 degree higher than our denominator. So remember, if we had the numerator was higher than the denominator, then we didn't have a horizontal asymptote. And that's because instead we have what is called a slant asymptote. Slant asymptotes are along that non-vertical, non-horizontal line. Like I said, they follow a y equals something straight line. And this is where our previous section comes back. The equation of the slant asymptote is the result of our numerator divided by our denominator, ignoring any remainder. So for our class, we're going to use synthetic division to talk about slant asymptotes. So if we want to identify the slant asymptote in this function, 4x squared minus 2x plus 1 over x minus 1, notice that our degree on top is x squared, so 2. Our degree on bottom is x, so 1. 2 is exactly 1 higher, so we're going to have a slant asymptote. So we need to divide by x minus 1. So here we're going to use synthetic division. These coefficients, remember to use zeros if you need to. Here we don't need to. And you're going to use a, so x minus a. So 1 is our a here. 4 is going to drop down for synthetic division. 1 times 4 is 4. Negative 2 plus 4 is 2. 1 times 2 is 2. And our remainder is 3. But we completely ignore the remainder here. We only care right here. And this gives us the coefficient of the next degree down. So x, we start with x squared, so we'll just go to x. We have 4. And yet again, I apologize, guys. I'm really getting quite angry with this. We're almost done, and it keeps wanting to kick me off. So again, we see our slant asymptote. If you look, there's also a vertical asymptote, but all we cared about for this particular example was that slant. You can see the vertical is going to be at x equals 1, which is right where we see it here. Now I want you to try. Find the equation of the slant asymptote for this function. Pause it, do what you need, and then you can move ahead when you're ready. So to get our solution, we're going to set up synthetic division with a equals -3, because remember x minus a. And our coefficients are going to be 1, -4, and 8. Drop that 1 down, have -3 times 1 is -3. -4 plus -3 is -7. And then our remainder is actually 29, but we don't care about that. So our equation is just the coefficients here. So we have x minus 7. And if we graphed it, we see something like this. Now notice when you graph on your calculator or anywhere else, you're not actually going to see these dotted lines. I have put them there to show you those asymptotes. But you'll see this purple part. You'll see like, oh yeah, that is laying right up across a line that's imaginary that we don't see. Never touches, never crosses. So there's one other thing that we can do with rational equations, which is something that it won't be overly new and you've probably done before. To solve a rational equation algebraically, there are a few steps that you're going to want to follow. The first thing you want to do is multiply both sides of the equations by the lowest common denominator, the LCD, to get rid of the fractions. So do what you usually do to get rid of fractions. And then you're just going to solve the resulting polynomial for x as you usually do. There's one little twist here, since we have places that are undefined when we're dealing with rational functions. Any solution for x you get, you need to go back and put it in the original version to make sure it's valid. If it's valid, you're good. That works. Otherwise, it's called an extraneous solution. And that happens when your x value that you find results in an undefined value. We just throw them out, okay? They're just not valid. So let's look at an example, okay? You may want to pause this and try, but otherwise you can just follow along. Here we want to solve for x, and x squared plus x over x minus 1 equals x plus x cubed over x minus 1. Notice that our fractions just have x minus 1 in the bottom. So the first thing we want to do is multiply everything on both sides by x minus 1. And we'll get rid of those fractions. So x minus 1 times that first piece and x minus 1 times that second piece. When we do that and we multiply it out, we're going to get x minus 1 times x squared when we distribute x minus 1 here. And then we're going to get plus x because this and this are going to cancel in that term. We do the same thing on the other side. We get x minus 1 times x. And then we get plus x cubed because this and this are going to cancel out. So you're distributing this whole thing as a whole. Now, if we multiply that out further, we can simplify it further. We get x cubed minus x squared plus x equals x squared minus x plus x cubed. Now, I like to pull everything to one side here at this point. These x cubes are going to cancel because x cubed minus x cubed. Negative x squared minus x squared is going to give us negative 2x squared. And x plus x is going to give us 2x. So pulling everything to one side, we'll get 2x minus 2x squared equals 0. And then we can solve for x like we usually do. 2x is in both, so we'll have 2x, and then we'll have a factor of 1 minus x equals 0. So now we've factored it. We just solved this as usual. 2x equals 0, and 1 minus x equals 0. So our solutions would be x equals 0 and x equals 1. But remember, we have a rational equation, so we're not quite done yet. We need to plug 0 and we need to plug 1 right back into the original to make sure we don't have an extraneous solution. So let's check 0. If we plug 0 into everything, we get 0 plus 0 over negative 1 equals 0 plus 0 over negative 1, which says, hey, 0 equals 0, which is true. We're good to go. So x equals 0 is a valid solution. When we do the same thing with 1, we end up with 1 over 0 here. That's not good. That's not possible. That's undefined. So x equals 1 is one of those extraneous solutions. We just toss it out. So our only solution here is x equals 0. Now, just like we've seen so many times already, we can solve this graphically as well. So maybe you don't want to solve it algebraically, or maybe you have the freedom to decide. Just plot both of them and look for the intersection. Okay, this can be a little trickier, you can see, because they can lay, you can see up here, they lay on top of each other almost, but then actually it's more like an asymptotic relationship. They don't actually touch and cross here. But we see here that there's a touch and a cross right there. Okay, and because of that undefined situation is why we see at x equals 1, that was our extraneous solution. We see that that's not a thing because that's an asymptote. Now, if we do these and press intersect, we can get exactly where those cross, which is right there, which is going to be, you guessed it, at x equals 0. Oh, that's it. I apologize for the technical issues throughout this. Greenville Tech's internet has betrayed me. But hopefully it was seamless. I'll make sure I listen to it before I post it. So rational functions are really cool, but they're kind of weird. So there's some rules that you need to follow, some rules that you're going to unfortunately just kind of have to memorize. But you want to make sure that you look for holes, vertical asymptotes, horizontal asymptotes, and slant asymptotes. Remember, not all of those will exist in all graphs. The holes are where you have factors that cancel from the bottom. Vertical asymptotes are where the bottom equals 0, where it doesn't cancel off. Horizontal asymptotes are based on the degrees at the top and the bottom. So if the top degree is larger than the bottom degree, there's no horizontal. If the bottom degree is bigger than the top degree, it's y equals 0. And if the degrees are the same, we have the ratio of that leading coefficient. Slant asymptotes occur only when the top is 1 degree bigger, exactly 1 degree bigger than the bottom. And we have to use that synthetic division to get the equation of that slant asymptote line. If you have to solve a rational equation, you can use graphical methods or algebraic methods. It's going to work very similarly to what we did before, except you need to make sure you check for those extraneous solutions if you're using algebraic methods. That's it. You're done with the material for most sections for this course. If 6.5 is the last one that you do in your section of 109, congratulations. You've finished and you've mastered everything you need to know. Study hard for your last test, study hard for your final, and I hope that you enjoyed the course. As always, you can reach out to me. There's all those extra resources available for you in our Blackboard shell, the Math Center, all sorts of things. And I hope that you guys have enjoyed this class. I've really enjoyed teaching it, and I've really enjoyed getting to know you. Thanks again. Thanks as always for tuning in, and I hope you guys have a great rest of the semester.